Hey, welcome everyone once again to our session here where we're talking about T-Shark and learning more about some of the things that we discussed in the Science SEC 503, the Intrusion Detection in Depth class. Once again, I am Nik Alleyne. I'm currently a director at Serious Computer Solutions, where I work specifically within the Managed Security Services business unit. Along with that, I'm the author of 2 books, Mastering T-Shark, Network Forensics, as well as Hack and Detect, where we leverage the cyber kill chain for network forensics. I also blog at securitynik.com, www.securitynik.com if you're ever interested in checking out that blog. And finally, and most importantly, I'm an instructor at the SANS Institute, where I currently teach the SEC 503, the Intrusion Detection in Depth class, as well as the SEC 504, the Hacker Techniques, Tools, Exploits, and Incident Handling class. A lot of what we will be talking about today is going to be associated to the SEC 503 class. So, if you'd like to get a lot more deeper into this content, feel free to come hang out with us at one of the upcoming sessions. All right, so without further ado, let's get going. First up, if you would like to follow along with today's content, feel free to check out the GitHub there. Stephen, who is working with me in the background, is going to be posting that link shortly. But you can go to my GitHub, you can select this repository. Come here, select this repository. And ultimately, they're going to be we will use the same file as we used last week, as well as there's another file in here. If I go to find, I see nmap_a. It is this host scan TCP. Okay, this file here, you can download this file, and this is the file we will be working with primarily today. Okay, all right, let's bring up our environment. And once again, this is fully hands-on and practical. Now, before we get going, last week, we spoke about reconnaissance at the network layer. Specifically, we spoke about ICMP protocol in detecting reconnaissance. Can someone tell me at what layer of the TCP/IP model does ICMP operate? Can someone tell me at what layer of the TCP/IP model does ICMP operate at? At the same time, whilst we wait on an answer, if we go to, let's say, RFC, let's say we go to the RFC, I see Ansiet says layer 3, Steve says layer 3. Let's scroll down to confirm or deny that. Now, the reason for asking this question is because when you use tools such as Wireshark or even T-Shark, you will see that it would seem like ICMP operates at the transport layer because it comes after IP. Okay, so just from a practical perspective, ICMP operates at layer 3. All right, let's clear that off now. Let's step back quickly to what we discussed last week before we move forward. Last week, the scenario was you and or I, or the new guy or gal on the team. Okay, let me just go to this folder. CD T-Shark. So you and or I, we're basically the new persons on the team. And in your case specifically, the senior team members asked you to do some threat hunting to confirm or deny a hypothesis, that being that reconnaissance occurred at the network layer. What we found last week was we used the file called nmap_snscan, let's say T-Shark, -n-r, and this was the file that we use. Okay, and what we did, we used a display filter to confirm, right? We say ICMP, let me put this in brackets, ICMP.type equal 8 and ICMP.code equal 0. Okay, and this allowed us to confirm that yes, this host here perform a ping scan against these hosts. But then the team said, you know, they've accepted the risk that once they have assets on the internet, it is more than likely someone is going to scan that environment. So what they were more concerned about were the responses. So what we did, we took the same command and now changed 8 here to 0. So this allowed us to see only the echo replies. So what matters here to us now are the hosts that responded, and this would be 103, 105, 106, 90, and 4. Let me clear the screen here and just run this again. So now the team asked us to dig a little further, dig a little deeper, you know, hunt further into the reconnaissance to see what else is occurring. So now we're going to move up to the transport layer to, you know, see what type of activities were done here. So to keep things simple, let's do it this way. Let's press up here. And let's copy these hosts. Let's put them in brackets also, right? Let's say we copy this host here. And I'll say IP.address equal. I paste that. Hi, Chandra Sakar. Someone just said hi in the chat there, so just respond in there. Okay. So we want that IP address, or notice the 2 pipes there, right? The 2 pipes represents or in this instance. And we can now take this IP address here. And notice also that as I specify these IP addresses, I am not specifying the source or the destination. I'm just saying IP address, which means I'm looking for traffic in either direction, right? Whether it is going to or coming from, I'm not interested, just once that IP address is involved. Now, similarly to how I use the 2 pipes to represent or, I could have also typed or, and I would put this in brackets, and I would say 106, let's see, IP.addr. Okay, once again, I'll put pipe just to mix it up to show you that you can do things differently. Let's say once again, IP.addr. Okay, and let's say finally, let me just add or here. So what this allows us to do is, this allows us to now focus on the IP addresses of interest. Because remember, if you are using a very large PCAP file, it is quite likely that you will not have time. Thanks, LinkedIn user. You will definitely not have time to be going through all of these individually, right? So you'll have to find some way maybe even to automate this process. But for now, we're trying to keep this simple for demonstration purposes and for ease of understanding. So now once we do that, let me actually clear the screen. What this would do is basically show us all of the hosts that communicated, right? So let's move away now from this file. Let's move away from this file that we were using for the scans, for the ping scan, to now look at the transport layer. So I would clear the screen, break out here, and if we do ls, this is the file you will be using today. And map host scan. Okay, this is the file we are using today. This is the file you can get from the GitHub. As always, if the team brings a PCAP file to us, the first thing we want to do is to take a look at that file to get an understanding of what is in that file. Okay, so we use cap infos, and we run that against the file. We can see information of first packet time, last packet time, encapsulation, number of packets, and so on. Now, because our concern is understanding what occurred at the transport layer, let's now take a look at the protocol hierarchy. And these are things that we also discussed last week, right? The second step, anytime you get a PCAP file, is to take a look at the protocol hierarchy. So I will say T# -R, okay, and then I will say -Z, IO, let me clear the screen, PHS, the protocol hierarchy, okay? And let me pipe this in more so everything does not scroll past the screen immediately. Welcome, Mary from Minnesota. So now, now, as you remember last week, right, when we use the ZIO, we have all of these here, all this information here, which ultimately we will see the protocol hierarchy, but to be honest, that is not what we're interested in. Class, welcome from Netherlands. Glad you're here. What we want to see is just the information of interest. So I'll clear the screen again. I'll say -Q. What that does is quiet out all of the PCAPs so that, or all of the packet records, so that I can focus on what matters, which is this, the protocol hierarchy. And as you can see, there's tons of data here, which suggests there's activity occurring at the transport layer, which gives us insights already. So the team wanted us to confirm or deny whether or not, port scanning was done, because we know for a fact that these hosts responded to ICMP echo requests. Now, if you're wondering why, let's step back for a second. I said previously that threat actors are more than likely going to perform a network scan first, maybe a ping sweep, and then ultimately take those hosts that they found. For example, for us, those hosts would be these IP address. The threat actor can take these hosts, put them into a text file, and then use that text file as input to a tool such as Nmap. And if you're wondering why I'm saying Nmap, remember, one of the tasks in the previous session was the team wanted us to profile the threat actor in terms of determining whether or not he or she was using Linux by default or Windows, or he or she was using some type of tool. Based on our analysis, we concluded that that attacker was using Nmap. So to help you understand, let's see, Nmap-help. Type this into more. If we look here, we can specify an input file, for example, for Nmap. So this is what I would have done if I were the threat actor here. So now that those hosts are scanned, we need to figure out, right, which host responding from the transport layer actually. Before we get there, let's figure out whether or not the threat actor actually scanned those hosts. Now, some of you might have heard about the TCP three-way handshake. In the TCP three-way handshake, can you tell me what is the first packet that is sent? Can someone tell me what is the first packet that is sent? Let me change this file here. Does anyone know what is the first packet that is sent as part of the TCP three-way handshake? Welcome, Diana from Uganda. All right, let me help you out here. So if I bring this up, and let's say I bring up, so here we have RFC 793, okay? Thanks, LinkedIn users. So the first packet that is sent is SYN. And let's confirm that, right? Let me just make things simple here. Let me just, okay. So here we are. Let's say this is the threat actor, okay? The first packet the threat actor is going to send to our devices within our infrastructure is a SYN packet. So what we need to do now is find the stimulus. So we need to go back here, and let's see, we come here and we say no, right? We want, and remember what we're looking for is these IP addresses, right? And now we want where the tcp.flags.syn is equal to 1. Because remember, right, if we go back here, we're looking for where the SYN flag is set, okay? Now, when we run this, we see, yes, we have packets where the SYN flags are set, but we still have a problem. We're looking for the stimulus. And here you can see SYN ACK, which means these are more than likely responses. These are not what we want. We want to stay focused on only the stimulus. So we now have to, let me clear this screen first, and run this filter again. And in running this filter again, we will say, and, or let me write and this time, and tcp.flags.ack equal 1. Now, when we say TCP flags.ack equal 1, we mean we're looking here for a situation where both the SYN and the ACK flags are set. This is, we're looking for the SYN flag and we're looking for the ACK flag. But realistically, that's not what we want. What we want is a situation where the ACK flag is not set. So I will put an exclamation mark at the front here. Okay? So once I put this exclamation mark here, we're saying, okay, we want the SYN flag set, but the ACK flag must not be set. Now, in some programming languages, some of you might have done something like this. All right, let me say exclamation. Would be something like that, right? Without the space. okay? But this is not how we use it in T#. So you need to ensure that you are doing equal sign, and this is why I also recommended last week that you put everything within brackets, okay? Now, when we press enter here, we now see that we have only packets with the SYN, which means we've all now called the stimulus. Now, to be honest, this is from the T# perspective, this is the right way to do it, what we just did here. From the T# perspective, this is the right way for you to do it. But we could also cheat, right? So let's cheat by removing here. I'll pipe this into more. If we pipe this into more, right, we can see what we have various information in these square brackets. So we can use something like that to prep for all of the SYN packets. So let's clear the screen. And let's say grep. Let's say we want to grep for SYN. And let me do this. Let's say color equal always. Now we can see we have SYNs all highlighted here, but we still have a problem. Similarly to what we did before, we have packets here with the ACK flags that are set, but we don't need that. We need only the SYN flag set. So what we can do now, we can come back here and say, you know what? I want to take advantage of Perl regular expression. And when we looked at that pattern, we saw that SYN was between the square brackets. The problem is these square brackets are actually part of the regular expression engine. So we want the regular expression engine to use these square brackets literally. So what I will do, I will say escape. So I will put a / in front of the brackets. And now you can see we have only the SYN packets that have been highlighted. So that is a quick cheat that I showed you there. Now, we've confirmed that the threat actor so far, or actually, let's go back here for a second. Right, let's come here. So what we have done so far, we have the ACK flag is not set. We have the SYN flag is set. But we're also looking at traffic from all of these different hosts. We need to confine this activity to only the threat actor's IP. So what we can do now is say, and IP.source. And notice in this instance, I'm not using IP.addr. I'm using IP.source because I want to only focus on 10.0.0.102, which represents, 10.0.0.102, which represents the threat actor's IP. So I'm looking only for traffic that is coming from the threat actor's IP into our infrastructure. Okay? So if we press enter now, come on, what are you doing? Remove this here. We press enter now, we see all of this traffic is coming from the threat actor's IP address. Okay, we can see 102, we can see 102, we can see only the SYN packet. So we see all the stimulus that are coming in. So the team might also want us to know what are the destination ports that were targeted, because any service that you want to interact with is more than likely going to be of a particular destination port. We can already see port 445, port 111 here, but what are the destination ports that have been, that the threat actor attempted to communicate with? Let's try to figure that out. Let's say, clear the screen here, and let's say -t, let's say fields equal, and which fields we would like to look at? Let's say TCP.dst port. And we can see we have a large number of ports scrolling by, right? But what are the unique ports? Because as we look here, we can see that, you know, some of these ports have been duplicated. We see 111 duplicated, 445. But what are the unique ports? What do? Clear the screen. We pipe this into sort, pipe this into unique. And when we pipe it into unique, let's also do some statistical analysis. Let's get a count of the frequency of the occurrences of these ports. Right? Okay, so now we still have a large number of ports, so much that they cannot hold on one screen. So let's take another step back. Let's find what are the top 10 ports that were targeted. And we can see that, one thing. Let's go back here for a second. Now that we have the count, let's sort it again. Let's sort it numeric. And let's make that reverse so the largest numbers can be at the top. And now let's look at the top 10 ports. Okay. Question is, can we have all possible, Shurat asks, can we have all possible lists of flags that and what that would mean? Shortly, I will provide you a list of some research I did a couple of years ago with stimulus and response, and that hopefully is going to be able to help you. Okay, so just give me a second, Shurat. So here now, we're finding the top 10 ports that were in use. Now, this is typically more helpful from an operational perspective, but from a security perspective, we might be more concerned with what are the least seen ports within our environment. Because think about it this way, on most days, we expect to see lots of traffic to port 80 or port 443 and so on. But those rare ports would be a cause for concern. So now let's come back here and let's say, okay, we see that all of these ports were seen in the environment. But how many ports in total did the threat actor try to communicate with us on? Let's say, wow, 1,000 plus ports the threat actor tried to communicate with us on. Now, if we go back for a second, right, let me see if I bring this up here. Let's see, Nmap. If you remember in the first session, we said, we concluded that based on the behavior of the Nmap tool, it was more than likely that the threat actor used that tool. And we're also seeing over 1,000 ports. Now, by default, as it says here, Nmap scans the most common 1,000 ports for each protocol. So that in itself says that it is more than likely, you know, along with everything else we have learned so far, that Nmap might have been used in this environment. So let's now move on. Now, we're talking about stimulus and response. So we know that the threat actor targeted 1,012 ports in our environment. But how many ports responded? Before we answer that, let's go back to the RFC. Okay. Now, as we look at the RFC, we know that, and actually let me ask you a question. So from a stimulus and response perspective, when I send you a SYN, if you are listening on that port, what should you send me back? When I send you a SYN, as part of the three-way handshake, what should you send me back if you are listening on that port? Does anyone want to take a stab at that? Now, whilst we wait on the answers, most of you might probably say SYNAC, and that is correct. But I would like you to also pay attention to something here. As you notice, let's say the threat actor at A, right, sends the SYN. What happens is the server or the device on the other end would acknowledge that SYN, right? And then the server sends its SYN. But when we talk about the TCP three-way handshake, what we're talking about is these two steps being combined. So the TCP three-way handshake is basically step one, these two steps combined, and then this step. So this is the three-way handshake. So what we would expect now is the SYN and the ACK packets. Now, let me come here. And this is where I answer the question asked previously. And I think Stephen is going to drop this link in shortly. So a couple of years ago, when I led the cybersecurity team, we had a team member that had some concerns or questions, I should say, about the stimulus and the response. So basically, the individual was looking at some flow data within IBM QRadar, which we support, and was not sure about how to understand the flags or how to understand the activity or the stimulus and the response. So what I did, I took a Windows 2012 system and a Linux CentOS 6.5. I had a port listening, and then there's a port not listening on both Windows as well as Linux. So when you send a FIN, what would happen? In this case, we're talking about the SYN. So when you send a SYN, it doesn't matter if it's Windows or Linux or any other device, it is more than likely it's going to send a SYNAC. And this is what we're looking at here. But to answer the question from previously also, you can look at this here now to see if you set various flags, what type of responses you would get. And this, do note, this was specific to Windows 2012 and CentOS, but who knows how newer operating systems might operate. And I'm saying this to say also that when you use tools like Nmap, it is these small nuances that these tools use to determine the type of operating system you have in use. Okay? So what we need to look for now is packets where the SYN as well as the ACK flags are set. So we come back here to our playground, And we now say, okay, let's remove all of these here. Okay. And what we need specifically are packets where both the SYN flag as well as the ACK flags are set. Okay. So we need packets where the SYN equal 1 as well as the ACK flag equal 1. But do note now, whereas previously we were looking for traffic that came from the threat actor's device, now we need to look for packets that are destined for the threat actor. So rather than IP source, we now change this to IP destination. So we can see traffic now leaving our environment and going back to the threat actor. Okay. And now we see we have a ton of SYN-ACK packets destined to the threat actor's device. We can see the 10.0.0.102, and these are all SYN-ACK packets. Okay. SYN-ACK. Now, we know also that the threat actor targeted over 1,000 ports within our environment. But how many of those ports actually responded? Let's try to figure that out. So what I will do is here, and let's say -T fields. In the previous example, we looked at the port where the threat actor was, or we looked at the ports that the threat actor targeted. That means we were looking at the destination ports. Now we need to look at our ports that are responding. So we need to look at the source ports. So I can say TCP.source port, right? And we can see we have a number of ports that responded. And what I will do, I will, once again, like we did before, let's sort this, right? Let's now put this into unique, get a count, and then sort it again, numeric. Okay, and we have the results returned here, but yet still, let's figure out one more thing. Once again, we know that the threat actor targeted over 1,000 ports. How many actually responded? Clear the screen, pipe this again into word count. Look at the number of lines that were returned previously. And what do we have now? 40. So out of 1,000 ports that the threat actor targeted within our infrastructure, specifically only 40 ports responded. So out of those 40 ports that responded, let's see if we can now find things that are of interest to us. Now, we will look at one encrypted protocol, specifically SSH, and we will focus the rest of the activity on clear text protocols, because realistically, clear text protocols is where we would find more interesting activities if we're doing network monitoring. So let's say we come here now, right? And we already know, right? We have these ports here. Let's say we wanted to grab port 22, for example. Okay? Let's say we wanted to grab port 22. What I will do, I will say, let's say we take advantage of grep. Grep is our friend. Okay? Let's say we do grep. Oh, sorry. Grep. And now I'll tell grep, I say, you know what? I would just like to grab port 22. Okay? Looks good there so far. What would have happened if I said I want to grab port 21? We can see now we have additional values returned, which don't represent what we need, right? What we need is only port 21. So this is where now and why sometimes you want to take advantage of regular expressions. Do note, and we will talk more about regular expressions later on in one of the series to show how we can use that with T#. For example, in the SEC 503 class, we talk about regular expression. I think we start off with it on day 1, we continue with it on day 2, but throughout the entire 6 days of the class, you will be using regular expression in one way or the other. So it's a very good thing to know, and we will have a session on using regular expression with T#, but you can also use it with other things, logs as well. So what we want to do, for example, in this case, is only get anything that has to do with 21, not 21, 21, or 21793. So I will come here and I will say, you know what? Instead, let's use Perl regular expression. Oh, and I was about to say also, if you have to use regular expression to solve a problem, you now have 2 problems, because first, you still have to solve your original problem, and secondly, you have to find a regular expression to solve your first problem. So if you can solve your problem without regular expression, you should definitely go that route. So what we want here is basically, we would like to find 21. And in finding 21, we can see here that 21 is preceded by a space. So I can say, right, if it's a space or a tab, give me that. But more importantly, even if I do this, we can see that we still have 21 here and we have 21 here. What we want is it must also end with 21. So what I will do, let me just bring this here, right? And I will now put a $sign at the end here to say I'm looking for anything that has a space followed by 21 and basically ends with that 21. Press enter. Now we have only 21. And we can do the same thing for, let's say, here. Let's say port 445, for example. Let me see, 22. Same thing here. Actually, before we move forward, let's ensure we have 22. Clear the screen. Let's do the same thing now. We can say plus 445, right? We want to end on that. Basically, what we're looking here for is common protocol, common clear text protocols, basically, right? Let's say we're looking to see if there's anything in here now to do with, let's say, LDAP. And, okay, let's probably wrap it up there, right? Let's just see 18. And we end with 80. Okay, so we have, except for SSH, everything else in here is clear text. So we can now filter down to get a better understanding of what occurred in these protocols. So let's start with port 21 that is typically associated with FTP. Now, typically when you have a large PCAP file, and once again, this is something we talk about in the SEC 503 class. If you have a very large PCAP file and you would like to get information of interest, you typically would write that information to a smaller PCAP file. So what we can do here, we can say T#. Actually, let's remove all of this here. Right, let's just remove all of this, and then we will use a display filter that focuses only on port 21. Okay. All right, so let's stay here. Once again, I like the habit of putting things in bracket. If you're running these commands on Windows, remember that single tick might not work. You might instead have to use double quotes rather than single quotes. I just like using single quotes, so this is why I use it here. So we can say our display filter is going to TCP, going to be TCP.port equal 21. What we're looking for is, be it is the source or the destination port, we would like to see traffic that is related to port 21. Okay. Now that I have this, I can just quickly run it on the screen. We see we have some activity. And once again, generally what you would do is write this out a PCAP file. Let's say we write it to temp, and let's call that file ftp.pcap. Okay. Now that we have that file, we can then run T# against it again, right? And we say temp ftp.pcap. And we have the information. For us, and in the interest of time, let's just do this. Let's look at the conversations. And let's say -qconf TCP, sorry, -q-z to get conversation TCP. Okay? And we run this, we see we have the various conversations show up. Let's just pick on one of these conversations. Specifically, let's pick on the one that says, all right, let me see here. Okay, we clear the screen and I will just type out one. Let's say, run this again. And in this example, we say follow TCP, right? ASCII. And in day 5 of the SEC 503, for example, I do a demonstration where we extract this content, not just in ASCII, but in RAW. And I will bring that example forward rather from, actually, let's put it this way. I will demonstrate that example next week when we talk about exporting suspicious content. So we will look at other things beyond ASCII, but for now, let's focus on ASCII. And what we want to focus here on is a particular session. That session is between 10.0.0.102, operating on port 33496, and 10.0.0.105, operating on port 21. Okay. Press enter. We can see now, let me just bring this up again so you see the command that was executed, right? Once we press enter, pipe this into more, we can see clearly into the clear text communication here, as in for the FTP. What do we have? We can see the username that was entered. We can see the password that was entered. We can also see the login was successful. Okay. Right away, we see the benefits of gaining insights into the clear text protocol. We can also see, for some reason, it says connected to, and we see 10.0.0.102. So it seems like the FTP server probably made a connection back to, has a connection with, our FTP server has a connection with the host at 10.0.0.102. Immediately, we were able to gain insights into the FTP communications there. Now, before we continue with the next clear text protocol, let's take a look at SSH. Now, you might be saying, but Nik, SSH is encrypted and thus we are not able to learn anything from SSH. To some extent, you are right. But SSH, like HTTPS, we are able to gain some insights before that communication actually becomes fully encrypted. So what might we be able to learn? Let's come here, right? And in the previous example, what we did was we did a filter for port 21. In this case, we're doing a filter for port 22, right? We can run here. We see the packets scroll by on the screen. Now, once again, in the previous example, we did -w and we give it a file, let's say temp ftp.pcap, for example. But do we have to write it out to the file system? Could we be more efficient? Could we maybe take more advantage of memory rather than writing to disk? Let's try that. So what I'm going to do here is say, hey, you know what? I would like you to write this output. But where would I like you to write it? I would like you to write it out to standard out. And this is what the dash does. Now, in the previous example, we also ran T#, right? But when we run T#, we run it against the file, for example, ftp.pcap. But we don't want that because we're taking the output from this T# command and using it as input to this T# command. So what we want to do instead is say we want to read, but we want to read from standard in. Okay? And now that we read from standard in, we should be able to see all of those packets. So rather than writing it to the pcap file, and then read it back from the pcap file, we did everything in memory. There's a question about similar heuristics. I'm not sure what the question is. Can you elaborate a little bit more? So maybe I can see if I can answer that. Okay. All right. Whilst we wait on a more extended version of that question, let's do this. What can we actually learn about SSH, even though this is an encrypted protocol? Well, let's see. We now come to -t fields. Which field we would like to look at? Let's say -e, the particular field is SSH.protocol. And to keep things simple, let's also sort this here. And as always, let's find the unique values. We don't have to, right? But I just like to get the count for the statistics. And then we'll sort this again, numeric, reverse. And we can see right away that, immediately we're able to gain insights into the SSH that is being used in the environment. So we can conclude that the device at the attacker's machine, where we know Nmap was being run, you probably attempted to use SSH 1.5 as well as SSH 2.0. And we can conclude also that the server is using OpenSSH 4.7, 4.7p1. So at this point, if you have this insight and there are known vulnerabilities against SSH, you can immediately go and try to take advantage of those vulnerabilities. So one of the application layer protocol we just looked in there too is SSH. We already looked at FTP. Let's say we take a look now at DNS. Why DNS? Well, because DNS is a critical protocol that is used in almost all of our infrastructures. I can't imagine you going to sans.org to look up information on the SEC 503 and not using DNS, okay? So similarly to what we did before, let's remove some of this information here, right? We're not going to write to disk. We're just going to keep everything in memory. And rather than TCP port 22, we can instead say TCP port equal 53. But that brings up a question for you now. What port does DNS use? And not sorry, not what port, what protocol does DNS use? Can anyone tell me what protocol does DNS use? Whilst we wait on the answers, right? What I will do here is I will say, okay, run this here. We can see various packets passing by on the screen, right? And we see information that suggests standard query and so on. Now, we do have someone that says said UDP. Both, we have Pradeep that says both TCP and UDP, and that's correct also. Now, on most days when you and or I are using DNS, we are going to more than likely use UDP. But for DNS zone transfer, for example, you might see TCP being used. But do note, and DNS is something we spend a lot of time talking about on day 3 of the SEC 503 class. If you have a DNS packet that is larger than 512 bytes, it is more than likely that that packet is going to be truncated, which means now that the truncated flag is going to be set in that packet, and that transaction will now have to be done over TCP. Now, to be honest, that was also true in previous times, because today you have something called EDNS, or Extension Mechanism for DNS, that allows you to have packets that are larger than 512 bytes. Specifically, the client can even advertise the largest packet it can receive. And typically, the client might advertise something like 4096 bytes. And if you were to compute that, that is like 8 times larger than 512 bytes. So the answer to the question is actually yes, both TCP and UDP. LinkedIn user said, while observing the steps you are demonstrating, it came to me that IDS probably executes similar, but in real time to validate this with you. So definitely the IDS will operate in a similar manner, because the IDS is operating, making decision on packets. And actually in the next section also, when I said the next section, session 3, we will talk about how I use one of those PCAP files to demonstrate some stuff around snort when we talk about the SEC 503. So come hang out with us next week, and we'll also talk a little bit more about that. But the IDS is going to make decisions on packets. Basically, we say packets or it did not happen. Okay. Thanks, Willem. EDNS 0 is the same thing I was talking about, extension mechanism for DNS. So what can we learn from DNS? Well, depending on the configuration of your DNS server, a threat actor might be able to ask your DNS server to tell him or her what version you're using. And I can say -t fields. And which field would I like to see? Maybe in this example, let's say, show me the source of the traffic as well as the destination. And in showing me the source and the destination, show me the query that is being made, right? Show me the query that is being made. So we can see here that we have query that is being done for bind. When we ask about bind, what are we asking about exactly? Let's say we add another field here, .e, let's say DNS.text, right? And we can see now we have information on Microsoft DNS that was being reported, right? We can see, and we say being reported because let's say, for example, that 10.0.0102 targeted 1090 with the version that bind, and we can see 1090 responded. Similarly, we can see information here which would suggest bind version 9.42, bind being the DNS server. So immediately you can see we can gain insights from the DNS servers in terms of their versions and so on. Now, you might be asking, how is this possible? Believe it or not, you can simply ask a DNS server for the type, let's say, for example, text, let's say chaos, and then let's say we want to do version that bind, and then you specify the name server. For example, let me see if I can get to this site here. Okay. And you see in this example, he says it's a secret. Most DNS servers today should be blocking this information, but the point is, you can see here that it says it's a secret. Now, let's go back also to the conversation we were having previously about EDNS, right? We can see EDNS is here, and we can see the 4096 here. Okay, we see EDNS, okay, right here, and we see 4096 here. All right, so we looked at DNS. We got a glimpse into DNS. We got a glimpse into SSH. We got a glimpse into FTP. What else can we do quickly? Let's say you want to look, for example, now at HTTP. And why? Because HTTP is like one of the most common protocols on our networks. And we know the threat actors IP, so I'm not going to continue with that. Let's say we instead make here port 80. Okay, and what field would we like to get out of here now? Well, I strongly believe that if you're doing threat hunting, you should definitely be looking at things like user agents and so on. So let's say we wanted to find out first. Actually, let's do it this way. Let's break this up into pieces. Let's do here, so you get an understanding of what we're doing, or better understanding of what we're doing. Let's say we want to do -q, that's the conversation, TCP, right? We have various conversations that are coming here. And for us, let's take the one that has to do with, let's take this one here, 50392. So I'll clear the screen. And I will say follow TCP ASCII. And what do we want to follow? We want to follow 10.0.0.102 on 50392. And the other side of that communication is 10.0.0.90 on port 80. Type this into more. And we can see now we have the clear text protocol, the fully reassembled session. We have insights into it right now. So let's now break down this here into, okay, Shurat says, impressed with skills, easy handling C# commands and keys. Wish to be able to do this. Do note the entire reason for doing this series is to help you to get better understanding of not just C# but packet analysis also. But by the time you finish with this, and if we do see you in one of the 503 classes, believe it or not, this would be as natural to you as it is to me. Willem says, I for one do keep forgetting those bigger than 512K. Thanks for the reminder. All good. So let's try to break this out now, right? What we want to do is, for example, how do we get the post? How do we get the path? How do we get the user agent? And do remember, right, as I've said many times before, our initial assumption was that Nmap is being used. And we can see many, many times now that Nmap is part of now the user agent. We saw it as part of the SSH information. We saw it as part of FTP information. So Nmap was obviously used heavily within the infrastructure. So let's now clear here. And let's say, look at some couple of fields. Let's say -t fields. Let me -t fields. And which field we would like to look at? In this case, let's start off with, let's say http.request.method. Okay, and we can see, let's just put it into sort, unique, clear the screen. We can see the methods that were used were get, head, option, post, and profind. Okay, now along with that, what was the URI that was requested? Let's say we expand here, we say -e. Once again, every time we would like to use a field, we use the -e, and we say -e, we say http.request.uri. Okay, and now we see the path that we're attempting. Okay, we can see, for example, the robots.txt might have very interesting information, right? We can see basically the root also was accessed. What about the user agent? Let's wrap up HTTP by looking at the user agent. And to keep things simple, let's also remove some of these other fields here. Let's say we want to focus specifically on HTTP. And where do we want to look? We want to look at the user_agent. Okay, and now we can see the only user agent that was seen had something to do with Nmap. This is being able to look at user agents is key as part of your threat hunting. Why? Because by default, a lot of these tools have their user agents, and the threat actor might not take the time to actually reconfigure or change it to something that is more representative of like a browser. Okay, so do note though that this information here can be easily spoofed. So you should not go relying on it as if it is the gospel truth about something being what it says it is, because I can easily change the user agent to represent something else. All right, let's prepare to wrap this up. Let's look at LDAP. If we come back here and we change this here now to port 389, okay, we can see we have traffic that is seen here on port 389. Well, how can this benefit us? Well, what we can do is, and once again, for simplicity, we're not going to follow the stream and all of these things. I've already shown you these things multiple times. But what we are going to do is take a different look. What are the LDAP attributes that are actually in this file? So what we can do, we can say -t fields, and let's say -e LDAP attributes. Okay, -t field attributes. Let me see. Oh, sorry. Let me just sort it. Unique. Okay, so we have, actually, let me add one more thing just so that it's clear. Let's say we add -e header equal yes. Right? So we have the LDAP attributes, and we have 22 of those attributes that have been returned. But what can we see about these attributes? Let's figure this out now. Let's say we extend on what we have so far, right? We say here, right? And let's say T#R, and let's say we put a display filter now. And what we want is, let's say, LDAP.attributes greater than 0. The number of attributes that are returned greater than 0. We have one file or one frame, one record, one packet that actually returned here, right? And that's frame number 16. Let's expand on that, and let's use the -v. Similarly to how you would see the full packet details in Wireshark, the -v in T# is going to allow us to do that. So let me pipe this into more. And you can see now you have the full breakdown. And as we scroll through, you can see various attributes are being reported. So for simplicity's sake, let's just run grep now on these attributes. So let's say grep, and let's say attribute value. Okay. And now that we have these here, let's pipe this into more. And we see immediately that we can see information on the domain, information about the forest, right? Zones, all of these information here is readily available in the PCAP file. And yet another reason why you might want to encrypt some of this communication. But obviously, if you're doing network monitoring, you have to be able to see into this traffic. But the point I wanted to make is that all of this information is still readily available. Let's wrap this up by looking at SMB now, right? So we come here and we change. Let's see here, are there any questions? Thanks, Arthur. Much appreciate the feedback. Thanks, LinkedIn user. All right, let's come here now, right? Let's remove these here, and let's change here to port 445. Because 445 is typically associated with SMB, okay? Now, one of the first things that occur within an SMB session is the host negotiate a protocol request so that they can determine the dialect that they're going to use. So if we wanted to now see what dialect the threat actor, let's see, IP.source, right? We want to see what dialect the threat actor was attempting to communicate with us on. We can say 102, right? And we can also look here and we say, we want to focus on the SMB command that is, let's say SMB, that has a value of 0x72, which is negotiate protocol requests, right? I press enter. Sorry, it says equal. I need to put 2 equal signs, okay? We can see we have a number of packets returned with the negotiate protocol request. But that is cool, but that is not what we want exactly. We want to know the dialects that were returned. So what I will do here, I will just clear the screen, and as always, we put a field. let's say, fields, and which field we would like to look at, smb.dialect. Okay. Now we can see we have a large number of dialects that have been returned here. Well, some of them obviously are repeating. So as always, let's tidy this up. Let's go sort, unique, right? And now we have just 2 rows returned. But even this here might seem a little bit clumsy for you to understand. So let's do a little bit of a trick, right, to prettify this or beautify this, whatever you want to call it. So what I will do here, I will say, use the Linux tr command, right? And what I want to do, I want to squeeze repeats, and wherever you see a semicolon, replace that with a new line character. Okay? And now we have a much cleaner view that we can take advantage of. Okay? Similarly to how we were able to find these here, we can also look at native operating systems that are in use by simply replacing the field. Let me move this here, clear the screen, replace the field here, and let's call this here native_OS. Remove this pipe at the end. Sorry. Okay, let me remove this here. By the filter, let's remove all of this here. Okay, focus on port 445 only, and we can see, right, we have Unix, we have Windows 5.1, Windows Server 2003, as well as 2008. All of this information we are seeing directly from within the PCAP file. Now, let's wrap up with this one here now. And this is an important concept for you to keep in mind also. All right, let's say we wanted to find where SMB version 1 is being used in our environment. Right? We want to find where SMB version 1 is being used in our environment. So what we can do here, we can say port 445, and specifically, I want you to show me, let's see, and smb.server_component equal, let's say 42, let me see, 0x42 4d53ff, right? And I will say -x and pipe this into more. Now, one of the reasons I brought this up is because here, right, there's a concept called endianness, little endian and big endian. And here, if you look at these bytes here, you can see 42 4d53ff. But as you look in here, you can see this is actually here ff53 4d4272. The bytes have actually been reversed. So you have to keep that in mind also when you're doing your packet analysis. Endianness, big endian versus little endian. And this is usually, you would have this concern whenever you have a multi-byte value. Along with that, I did this example to show you that if you're in your environment and you're seeing that byte sequence, if you're seeing the byte sequence of this here, note you're running SMB version 1. And for no reason should you be running SMB version 1 now because of the vulnerabilities. Okay? All right. This is basically the end of this session here. I think we did a lot talking about application layer protocols today. And actually, let me just take a quick question here. It says, do you happen to have all of these hunting packet captures commands in one place? Absolutely. The packet captures are in GitHub. Stephen shared the link earlier. So all of the PCAPs are right there. All right. So I was saying that we started off last week where, as the newbie on the team or the new person on the team, the senior guys and gals wanted us to do some threat hunting to determine whether or not reconnaissance was performed against our infrastructure. We confirmed that last week in that reconnaissance occurred at the network layer using ICMP. This week, we looked at now reconnaissance at the transport layer whilst also learning about some application layer protocols. Next week, we have something even more interesting. Next week, we're going to look at how we can extract suspicious content from the PCAP file. We're going to do it from 4 different perspectives where T# understands that there is something in there in the PCAP file, where T# does not understand, and we will reconfigure T# to now recognize this, this suspicious content. We'll do it from a perspective also where T# just does not know anything is there, and we now have to use third-party tools in conjunction with T# to extract this content. So it's going to be a very exciting session next week, and we hope that you come hang out with us in that session. So thank you for hanging out with us this week. Hope you enjoyed the session. If you have any questions, hit me up on LinkedIn. The GitHub page has everything you need in terms of the PCAP files, right? This is my GitHub page. Everything you need is right there. Yes, these are available. I'm not sure if it's available for download, but definitely they're online. And Sans is going to put together a playlist to tie this in conjunction with the SEC 503 class, so you have this guidance whenever needed. Thanks, Douglas. Much appreciated. Thanks, Pradeep. Definitely appreciate the feedback. Thanks, Arthur. Much respect also. All right, so see you all next week, and hope you all enjoyed the session. And feel free to share with your friends, your colleagues, and let them know that next week's session is going to be even more amazing. You will really enjoy next week's session. So see you next week.